I think he's an Italian. Yes. So this one, earlier we, let me recall what we have done. Say if we consider a system like this, and these are two loadings, and the two loading doesn't have to be symmetric. So in general, it could be like this. So the loading conditions we have learned is this. And we can try to apply the loading P1 first, slowly, and to get the deflection into equilibrium, and that corresponds to this curve. And upon this, at point 1, this is point 1 here, let me call point A, point 1, and this is point 2. At point 1 here, we, according to our notations, this would denote that this is the x at location 1 due to loading 1. At point 2, we have the diffraction at point 2 due to loading 1. Yes. And then subsequently, we added up the second loading. And again, the loading applied is quasi-statically, so that means slowly. And contribution of the second loading to the overall will be described by the green curve. In the meantime, P1 is keep applying. So that is the deflection by this. Okay, and now this one is, per our notation, is the deflection at point 2 due to loading 2. This is the deflection at point 1 due to loading 2. Okay. So the overall deflection, this is deflection at point 1. The overall deflections, this is x2. Okay. So that's what we have done. And last time we spent examples to calculate x1, 1, 2, 2, whatever these things. This concept can be applied to any type of the loading frames and with the different type of the constraints. And the loading can be really as a point loading, or the loading can be a moment. Okay, and we will see by more examples here. So last time we have learned the total strain energy upon those scenarios will be equal to alpha 11 P1 squared plus 2 alpha 12 P1 P2 plus alpha 22 and P2 squared. And here the alpha 11 12 alpha ij simply is defined by the xij divided by p. I don't have to go this one. For example, alpha 11 equal to x11 divided by p1, and alpha 12 equal to x12 divided by p2, and alpha 22 equal to x22 divided by p2. Okay, those are the definition, and we call the alpha is called the compliance. That is what we have done before. And now, furthermore, I have one more step, and actually this is an important step, is this. This theorem mentioned that the displacement at any positions, and here we have the two locations where the loading applies. The deflection at either of the place j equal to 1 or 2, this indicate the location where the loading applies. And here we have two loadings, so we only have the legible two places. If we have three loadings, then j equal to 1, 2, 3. Okay, this one can be calculated by this derivative of this respect to p j. Okay, so that is what the theorem mentioned. Okay, and we can see why. For example, we do the calculation partial u, partial p1, see what happened. And now we do the calculation here. And partial u, partial p1 basically will be equal to alpha 11 times p1 plus this alpha. Are we okay? Again, upon the whole expression, I simply take the partial derivative with respect to p1 and then get this result. And what is this one? This one, per our notation compliance, this is alpha 11, this is alpha 12. And what is this? Sorry, x11, x12. x11 plus x12 equal to the displacement at this point. So we prove this one, and we can repeat. If you like, we can do one more time, partial u, partial p2. We see what happened. Per this equation, basically taking partial derivative with respect to p2, that will be alpha 12 p1 plus alpha 22 p2. Okay. So this one is x12, this is x22. So this takes dimension, this is x2. So the question to Sarah's email, I hate that emails came to bombard me every morning and then that shake me up. Kidding, I'm kidding. But that question, that email pretty, I think that's very good. And what was the contents of the email?
My homework?
Yes, of course. You have nothing else, right? I only look at the homework part.
You're
yes.
talking about like the 1 versus 2 loading, or?
The Sarah's email asking for examples of the multiple loadings. Are we able to, for example, if we want to calculate diffraction at point 1, are we able to calculate using this formula? And that in her email, is this okay? This is the approach we learned in the first portion when the system is under single loading. Only have single loading. In the single loading, the total strain energy will be able to equal to the loading multiplied with displacement divided by Q. Okay, but for multiple loadings, is this method still good? If we have multiple loadings, are we able to say, if we want to calculate displacement at x1 using this formula, and if we want to calculate displacement at x2, we use this formula. Using the same amount of the strain energy applied to the different templates of borrowing the concept from here for the multiple loading, I don't think this is right. Because you can see this strain energy, what we have done before is, if there would have a single loading, then we have no such two terms. If there's only single loading, the two terms will disappear. Then you can see basically this formula for single loading is what we have the concept before. But we have a multiple loadings, then this term will give us kind of the nonlinear coupling. So Sarah, in your emails, I think that kind of inspired for more thinking process.
You're talking about the second one, right? The second email, not the third email that I sent.
See, okay, that's the evidence. You bombarded me for how many emails admitted. Okay,
maybe I want to get the homework done. It's due Monday.
I'm only paid by that much by the university, and then I have to endure the midnight bombardment from students.
All right.
Okay, that's still recording. Then hopefully someone can help me, the president. Okay, I'm asking for a raise.
Which problem?
Either one, because those ones for the multiple loading case. Yeah. But anyhow, and back to our questions.
So
And
how do we correctly do it then?
yes, again, before Wednesday, that's what we have learned. For the single loading case, we're using this case. We're using, if we want to calculate what is the diffraction here, let me call it delta. 1/2 divided by multiply P delta equal to the total strain energy. This is totally fine. This method won't be applicable to these multiple loading cases. Okay. Because of this term. Because of this term. Okay. And this method, this formula is a special case. This method is a special case of this theory. I would say so. Okay, so I think maybe for the next time when I teach this one, I will start from here right away, and then go to here, because that could be maybe more logical. Okay, this is a special case of this one. So from now on, I would recommend when you think about using energy method to solve for diffraction, think about this one. Okay, this one, basically you take the partial derivative of the loading. Basically, you can see this one. If I can apply, you can say this one U will be equal to 1/2, and delta equal to how much? Delta equal to whatever. Using my office hour, I can explain that to you. But anyhow, we stick with this one. Okay, keep this in mind, and then we can take a look at examples here. And again, for this case, the P, I want to make a comment. The loading can be force or can be moment. So for example, if we have, if we have the structure like this, and if I apply the loading P here, and also I apply the moment at this free end by M, okay? So corresponding to those kind of loading, say the condition could be something like this. So corresponding to this loading type, we have diffraction, let me call the delta. And corresponding to the loading N here, we have the corresponding diffraction, which in terms of the moment here is theta. Okay, that is the corresponding physical quantities of the deformation to the different loading type. So for this case, if you be able to calculate the total energy, then you can calculate delta should be equal to partial U, partial P. And then again, you can calculate the corresponding change of the deformation, and there is partial U, partial M. Okay, so here the note I want to make is the X represent is the deformation. Deformation has basically a general rule, either displacement or angle, depends on the type of the loading. Okay, so that's the principle, and then we can take a look at the examples here.